Hello, in this video we will be going over Java sorting algorithms. We'll be going over about 6 of them, and we'll also be talking about their big O notation runtimes. Um, big O is basically a way to talk about the speed at which an algorithm can run, and it's notated by an O followed by parentheses, and then the speed is written in here. So if it's linear time, it would be ON, constant time would be O1. If it's n squared time, it'd be O(n) squared. So there's just examples of big O notations. So first, the first sort that we're going to do is selection sort. So selection sort is when you will scan the array that you have, and then what you're going to do is you're going to find the largest one and then move it to the end of the array by doing a swap. So first, when we're looking at this array, we see that out of all of these, 21 is the largest. So we're going to swap 21 to the end and swap 21 and 14. So then the next iteration of the array becomes this. So that's the first step of selection sort. And then if we just keep going through with that process, but now we only look at these elements in between 3 to 14. So the next largest element is 19. So we're going to swap 19 with 14. So it becomes 3, 8, 14, 5, 3, 19, 21. And we're just going to keep repeating this process. We're going to swap 14 with 3. So it becomes 3, 8, 3, 5, 14, 19, 21. And then these 3 are blocked off. We're going to grab 8, swap it with 5, 3, 5, 3, 8, 14, 19, 21. Those 4 are blocked off. Now we're just looking at these 3, 3, 5, 3. 5 swaps with 3, 3, 3, 5, 8, 14, 19, 21. This is our sorted array with selection sort. And its runtime is a big O notation of O(n) squared. Kabang. Okay, the next one that we're going to do is insertion sort. So unlike selection sort where we grab the biggest one and moved it to the end, in insertion sort, we're going to start by looking at these first 2 elements. We're going to put them in order, and then we're going to expand to include the 3rd element, the 4th element, and so on until we get through the entire array. So first, when we're looking at 3 and 8, we see that it's already in order, so it becomes 3, 8, 19, 5, 9, 20, 12. And 3 and 8 are locked in. And now we're including 19. We're checking 19, and still it's already in order. So this next iteration is the same again. So now we have 3 numbers locked in. Now we're going to put in 5, and we're going to scan it to see where it belongs. And we're just going to keep moving 5 until it'll eventually fit in its correct place. So now it'll become 3, 5, 8, 19, 9, 20, 12 with 4 elements locked in. Now going on to 9, or that goes in between 8 and 19. So 3, 5, 8, 9, 19, 20, 12. Adding in 20, it's already the highest value, so the array stays the same. This time it's added with 20. And finally, we're adding in 12. So 12 will fit in right here. So the final array will be 3, 5, 8, 9, 12, 19, 20. And that's the sorted array using insertion sort, which, similar to selection sort, had a big O notation of n squared. Shabang. Okay, so next up we have a bit more of a complicated algorithm, which is called quicksort. And although it's quick for the computer, it's kind of hard for people to learn. But the essential idea of it is that you're going to pick a pivot number in the middle, and then you're going to analyze the values to the left and to the right, and based around this pivot until everything is sorted out. So in this example, we're going to label the left side I, the right side will be J, and this pivot here in the middle is going to just be labeled as P. So the first thing we do is we look at J, and while the value at J is greater than or equal to the pivot, you're going to keep moving the J variable to the left. So 12 is greater than 5, so we move to the left. 20 is greater than 5. 9 is greater than 5. 5 is greater than or equal to 5. 19 is greater than 5. 8 is greater than 5, but 3 is not. So now J is here. And on the other hand, when you're looking at I, you're going to move I to the right whenever I is less than or equal to the pivot. So since 3 is less than 5, we're going to move I once here. So now we have that J is here, I is here, and the pivot is still where it is. Okay, so now that we have the new places of J, I, and P, what we need to do is swap this pivot value with the I value to make it in order. And essentially each step of this algorithm, you're locking in the position of the pivot. So in this case, after we perform a swap, the array will look like this. And the value that's locked in is 5. Now I know this may seem confusing, but we're going to keep doing it as we go through this array, and hopefully it'll start to make more sense. So after we do 5, this is actually a recursive algorithm, which means that it'll do the same thing on the left side and on the right side. So looking at the left, it's pretty simple. It's only 3, so 3 will be locked in. And now if we're looking at the right side, we're going to do the same steps up here. So I will be on the left, pivot will be in the middle, J will be on the right, and we're going to move J to the left as long as this value is greater than or equal to this. So 12 is greater than 9, 20 is greater than 9, 9 is equal to 9, but 8 is not greater than 9. So J is going to be here. Now when we look at I, remember we move I whenever the value is less than or equal to P. So 19 is not less than 9, so I is going to stay there. Now in this case where I is still to the left of J, what we're actually going to do, instead of swapping with the pivot, we're going to swap between these two variables here. So we're just going to swap where I and J are. And now J will be here, I will be here, and P is still there. And now what we're going to do is we are going to swap P with I. So these two are going to swap locations and it'll become 8, 9, 19, 20, 12. And now the pivot is locked in. We're going to split it to the left, to the right. 8 is by itself, that gets locked in. And we're going to repeat the process for these final 3 elements. We're going to move J whenever it's greater than or equal to P. Doesn't move at all. We're going to move I whenever it's less than or equal to, which it moves, and then it moves again, so I becomes here. Now that we have this position, we are going to swap P over to where J is. So it becomes 19, 12, 20. Remember, we're locking in the pivot, so since the pivot was 20, 20 is the one that gets locked in, which just leaves 19 and 12. And now if you have an even number, the pivot is always on the left side. So I, P, and J. I is going to move once to the right. J is not going to move, so now you have J and I here. So now P is going to swap with J, so it becomes 12 and 19. Since 19 is the pivot, 19 is the one that's locked in, and then 12 gets locked in at the end. So your final array becomes 3, 5, 8, 9, 12, 19, 20, which is in the correct order. That is the quicksort algorithm. And although that seemed to take up a lot of space and like run speed, the actual big O notation of this is O n log n. And if you don't know, log n speed is actually uh, better than n speed. So remember, selection and insertion sort were n squared, which is actually going to be a worse run speed than n log n. So quick sort is actually faster than selection and insertion. Boom. Moving on to our next algorithm, it's another recursive one called merge sort, where basically the array is constantly halved until there's very small pieces of the array which are slowly scrambled into the correct order, and then all the parts are put back together into a fully ordered array. So first off, we have to have this array, so we're going to split it down the middle. And so now we have this half, which is 3, 8, 1, 5, and the second half, which is 9, 20, 12. And then we're going to split it a second time, so we're going to split this. We're going to split this section. So now we have 3, 8, 1, 5, 9, 20, and 12. So now, if we first look at this section here, we have to order 3 and 8. And luckily, 3 and 8 are already ordered, so we can just leave that how it is. And that's ordered. Next, looking at 1 and 5, those are already ordered as well. Now moving on to the second half, we look at 9 and 20. Those two are already in order. And then 12 is by itself, so it's good. Next, what we need to do is merge these two together and put them all in order. So then this will become 1, 3, 5, 8. And then on this half, we have to merge these two halves together, so become 9, 12, 20. And then finally, we're going to merge these two big halves together to become 1, 3, 5, 8, 9, 12, 20. So that is merge sort done. And similar to quick sort, the big O notation is once again n log n. Last one is going to be tree sort, which involves some more complicated concepts with balanced binary search trees. And if you don't know what that is, you will have to watch another video because this is only my second video. So go have fun watching that. And once you come back, we're basically going to build a binary search tree for tree sort. So before explaining the parts of the algorithm, we're just going to draw a balanced search tree with this array, a balanced binary search tree. So 8 will become our root. All the smaller values go to the left, while the larger values will go to the right. So we're just going to build this tree right here. And luckily, this tree is already balanced because the heights of the left subtree and the right subtree don't differ. They're the same height. So since that's happening, we know that this is a balanced binary search tree. And from there, all we have to do for this algorithm is always grab the smallest value, which is going to be on the leftmost side, and then plug it in to our new array. So grabbing 3, and then 5, and then 8, and then 14, and then 19, and then 21. So this is our final array with tree sort. And similar to merge and quicksort, the big O notation is O n log n. So it's overall a pretty simple algorithm as long as you know what a balanced binary search tree is. Okay, so the final sorting algorithm of this video is called radix sort, which typically involves large numbers that go into the hundreds, where basically the point of the algorithm is that it'll first scan the ones place of all the values, then the tens place, and then the hundredth place. So pretty simple. First we're going to write the ones table. So all the numbers that can be in the ones place are these digits. And now we're going to take each element from this array here and we're just going to file it in to where it belongs in this ones table. So 121 ends with 1, so it'll go here. 235 ends with a 5. 312 ends with a 2. 341 ends with a 1. 241 ends with a 1. And 156 ends with a 6. So from there, we're just going to put all of these values in order into a second array. So we start with 121, and then we have 341, and then 241, and then 312, and then 235, and then 156. So now we're going to do this again with the tens place. We're going to do tens, and all the tens digits can be this. And we're going to file through this new array again, but this time looking at the tens place. So 121 has a 2, 341 has 4, 241 has 4, 312 has 1, 235 has 3, and 156 has 5. So now we're going to move all these values into a third array. 312, 121, 235, 341, 241, 156. And finally, we're going to do one final table with the hundreds. And these are all the digits that it can be. Oh, 6. So looking at the hundreds place now, 312, 121, 235, 341, 241, and 156. Well, now, when we move all these into the final array, 121, 156, 235, 241, 312, 341, we see that is a fully sorted array using radix sort. And funny enough, this sorting algorithm actually has a big O notation of ON, so it is a linear search runtime, which is fast, but it is only able to have ON runtime because this sorting algorithm is mostly limited to integers. Thank you so much for watching. I hope this video helped you with sorting algorithms, UCS majors. Yes, bye-bye.